I'm Gan Pereira. So today we are going to do a lesson which is out from mathematics, but it is really helpful those who are working with data and also the professionals those who are making decisions based on data. So this is simple linear regression. So first I will discuss the theory part and later I will show you how to use Microsoft Excel to perform the simple linear regression and how to interpret the result of Excel. So let's directly go to the lesson. So you can see my screen now, right? Simple linear regression. So what is simple linear regression? The concept of simple linear regression, and we will discuss limitations of simple linear regression, and later we discuss how to use Microsoft Excel to perform the simple linear regression. Just look at this graph. So this is called a scatter plot. So one variable is in x-axis, the other variable is in y-axis. So all the data points are mapped, and thereafter we put a line which is going through the points, but it doesn't cover each and every point. So, but this will be the maximum possible line which should cover the variations of the points. So, from this point only, the simple linear regression arises. So, in terms of mathematically, if you look at the line, basically the equation is y equals mx plus b. What m is, it's a gradient, and b is the y-intercept. So that is the basic concept of straight line in mathematics. So let's see what are the limitations of simple linear regression. So we assume that there is a linear relationship between independent variable and the dependent variable and residuals. So there's a new term, residuals. Residual means error. So error means it's a difference between the actual value and the predicted value. So we assume the residuals are independent. And homoscedasticity, that means the residuals have constant variance at every level of x. X means the independent variable. And also we assume our residuals are distributed normally. So look at these two graphs. So first one is straight line, which is drawn according to the mathematics. So according to mathematics, each and every point should lie on the line. So when you come to the statistics, so this line of best fit, you can see line goes elsewhere, the points distributed around the line, but each and every point should not exactly lie on the line. The lines which drawn vertically are basically the error. So red line is the line we fit, that is called the fitted line, and the distance between from line to the point is basically called error. In other terms, it is residual. So basically we can identify three types of straight lines, which is ascending, which is descending, and which has no ascending or descending. So when it come to the equation, so when it's ascending, the gradient is positive, which is beta 1 is positive. And when the line is descending, the intercept beta 1 gradient beta 1 is negative. And the line is not changing over the area, so gradient is 0. So beta not represent the basically it's y-intercept. That means the line where the line cuts at the y-axis. So the definitions are actually same as mathematics. So no difference between the definitions. So this is the equation as I told, y equals beta naught plus beta 1 x plus epsilon, that is error. This term defines the error term, right? X is independent term, y is dependent term. So independent term explain the dependent term. So that is what regression line do? Let's see what is this ordinary least squares method. So I told you now there is a error. Error means the difference between the actual value and the fitted value. So when you get the difference, that is what we call error. So now if you can remember the previous graph, there were some points above the line, some points were below the line. So when you get the difference, sometimes you will get positive differences, sometimes you will get negative differences. So what happened when we add them together? So basically, according to the mathematics, when you add positive and negative numbers, they will cancel each other. So the sum will be then basically approach to the zero. So therefore, to eliminate that problem, what we do is we get the error and we squared it. When we squared it, whatever the error, positive or negative, squared term is always positive. So then we will get the sum. And we fit the line such that this sum of the squared errors is minimum. So that is what we call ordinary least square. So in this graph you can understand. So this is what we say error, and this error will be positive, and this, when you come down, this error will be negative, and when we add this together, so it will cancel each other. So in order to avoid that problem, we square the error terms. Right, let's move on. And these formulas actually no need to remember, but these are the formulas which we use to calculate. So mathematically, these are the formulas which we use to calculate the linear regression. So B1 means the approximate for the beta 1, B naught means the approximation for beta naught. So whenever you go to calculate beta B1, you need X bar. So here it says how to calculate the X bar. And when you go to calculate B naught, you need Y bar, X bar both. So here are the formulas to calculate X bar and Y bar. And SSE means the sum of squared errors. So this is the term which we call residual. See, here we squared. That's the thing we discussed earlier. Right. And let's see what is the new thing. R squared. This is a coefficient which we calculate to determine whether our regression line is good to use or not to use. So based on this R squared value, we determine the strength of our regression line. So R squared can take any value in between 0 and 1. If you get 0, that totally there is no linear relationship between the two variables. If we get 1, that's there is a perfect linear relationship between the two variables. So now you understand, we can get any value in between 0 and 1. When the value close to 0, the linear relationship goes away. When you go towards the 1, the linear relationship comes towards, that means become stronger. Look at these graphs. So there's scatter plots. In this first one, you can see the dots are everywhere. There's a line going in between, but there is no linear relationship between these two variables. That's why R is 0. And in second graph, see, it's a curvage. So for the curvage, if you fit a line, it never explains the relationship. So R is 0. So in third graph, you can see there's a clearly all dots are lying along the line, and it's also descending. So that's why it's is to -1. And here it's goes to upwards. So R is then equal to 1. It's all the points are on the line. And here R is equal to 0.4. So points are little away from the line, but still there is an upward trend. But it's actually it's a weak relationship. See, it's close to 0. And it's -0.3. It's going little downwards, but most of the points are so much away from the line. And when you come to this one, it's much closer to the line and going downward. So R is equal to minus 0.8. So r is equal to 0.8, it's going upward and much closer to the line. So r squared and r is different. So r squared is can take between 0 and 1. R can take -1 and +1. 0 to -1 line goes downwards. 0 to +1 line goes upwards, right? So closer to 0 from either sides, weaker the relationship. If goes to the +1, stronger this relationship and its upward trend. And the value is closer to -1, line goes downwards and stronger the relationship. Okay, now let's move on to the Excel, and let's see how Excel will give us the regression output. So in order to module this Excel output, I downloaded some data from Central Bank of Sri Lanka government site. And now let's move on to the Excel file. Right. So here I have selected some data, right? So based on the month, so I have extracted the data, the country's average weighted lending rate and average weighted deposit rates. Average weighted lending rates and average weighted deposit rates. So I basically took average weighted deposit rates as X, the independent variable, and I took the average weighted lending rates is Y as the dependent variable. Now let's see how to run the regression. So before run the regression, it's prudent to obtain a scatter plot and see how data distributed. Okay, so let's select the data first and then go to the insert. And if you want, you can go directly go to the recommended charts. So they will show you a lot of charts. And if you want directly, you can go to this scatter plot and select this. So this is the scatter plot. So you can see there is a upward trend, right? So there is a upward trend. Now let's see, once we fix the Excel equation regression, so do we get the same result from the regression outputs? Okay, now let's move to data analysis. And when you go to data analysis, there is a tab called regression. Select regression and then press OK. So here we need to select Y variable first, right? So my Y variable is this one. So I select that, the whole data, and then I go to X range. So I select X range. Remember, there is a level of confidence. So I take basically in most of the statistical outputs are 95% confidence level is enough. So therefore, I take 95% confidence. But if you want more confidence, you can go up to 99 by selecting this. So right now I'll stay at 95. And if you want, you can get your output to a new Excel sheet or new workbook. But I will take my output in the same sheet somewhere closer here. Right. See, now we get the Excel output. And now let's go and identify and interpret this result, right? When you get the Excel output, before go to anywhere, just go these two cells. What is that? It is nothing but R squared and adjusted R squared. Look at the value. It's 0.96. Even adjusted R squared is 0.96. So that means there's a very good positive relationship. So we are good. We are very good to use this output as our regression line, right? And here we have the two variables, intercept and X variable. So now how do we write our regression equation? It's Y equals, the coefficient of X is, see, 1.055. So let's get to the two decimal places, X, and plus 4.055. 7 4 7, so let's say 7 5. So this is our regression equation. Okay, now sometimes some results, if you want, you can use this confidence interval. Let's see what is confidence interval. So you can see two lower 95, upper 95. So that means the lower bound and upper bound of these two coefficients, 95 means that's the confidence level we have selected, right? Okay, now let's use this equations predictor value. Okay, let x equals the interest rate. Let's say we predict okay, 10% is not there. Let's predict 10%. Let's see what is the output. So how to get the output? 1.05 times 10 plus 4.75. So then if the average weighted deposit rate is 10, then the predicted average weighted lending rate should be 15.25 according to our regression output. What is the confidence level? So we are 95% confidence. So our average weighted lending rate will be 15.25. So this is a single value. Let's see if a manager want to predict an interval without predicting a single value. If you want to predict an interval for this one, so let's use this thing. So first of all, get the lower 95, right? Lower and upper. Okay, so what is the lower equation? Y equals, it's 4.19 times x. Wait. So it's 0.98x plus 4.19. And what is the upper one? So y equals 1.12x plus 5.31. Right. Okay, now let's predict the lower value when x equals 10, right? When x equals 10, 0.98 into 10 plus 4.19. 1.12 times 10 plus 5.31. See, now it's 13.99 to 16.51. So what is the meaning of that? So we are 95% confidence when x equals 10, average weighted deposit rate is equal to 10, the average weighted lending rate would be in between 13.99 and 16.51. So that is what confidence interval. And this is a single value. This is a interval. I think you understood it. And I will upload this Excel sheet in a document section for you to download and to get the reference. Right, now let's see what is this residual. So residuals is the thing we discussed earlier. Okay, let's see what is the sum of the residuals. Let's take two. See, when you get to two decimal places, the residuals in sum is 0. Okay, so I told you we get the squared of the residuals. Let's square it. So get the square and let add them together and see. See, look at the squared sum of the residuals is 12.6764. That is what SSE. I think you understand why we cannot get the direct sum and why we are getting the squared sum. Okay, so I have selected another variables. The first one is still the average weighted deposit rate, and secondary worker remittances. That means those who are going outside of the countries and send money to the country. So that variable I have taken as USD millions, and this is as percentage. Okay, let's see, is there a relationship between these two variables? As I told you, first attempt is to obtain a scatter plot. Insert scatter plot. Look at this graph. The points are everywhere, right? So basically, if you just look at this, so you should understand the linear prediction will not be work on this, right? So let's go to the regression output and see whether it suggested the same result. Data, data analysis, regression. Okay. Okay, so my Y range, Y is average, Y is my worker remittances, and X is my average weighted deposit rate of the country. So my confidence level is 95, and my output, I will get the output to here onwards, and I get the residuals also. Okay, right. Now look at this R squared and adjusted R. See, it's 0.01 minus 0.01. They are very, very close to zero. So as I told you before, there is no clear linear relationship between the two variables. So if someone is assumed that based on the country's interest rate, people outside the country are sending more money to the country, so that result is not valid based on this result. So that means people are sending money to the country is not based on the country's interest rate. So that is what this output suggests. So there is an intercept, everything is here, but you can make an equation, but equation is not valid to predict results. So that is the problem, right? So if you look at the confidence interval, you can see the two upper bound and lower bound are far away. The interval is too much wide. Why? Because this R squared is close to zero. We cannot assume a linear relationship. Therefore, this interval is very, very wide. So if you go to our previous example, see the interval is not that wide. See 4.19 to 5.3, it's small, right? So this interval is very, very wide. So why? Because it cannot predict a clear linear relationship. So I think you understand this, and I will upload this Excel sheet for your reference. You please go through it. And if you want more clarification, I will give you. And so I think now we are come to the end of our today's lesson. So what we have learned, so we now learn what is simple linear regression and for what purposes we use it, and we use Excel to obtain the simple linear regression. Okay, so what will be the next video? So just think, so today we had just one X variable, one independent variable. If we have 2-3 independent variable, what can we do? Okay, so if you want to look at this, let's come and join with my second video. There is nothing but multiple linear regression.